Exercise 2. The number of primary alcoholic isomers for C4H10O is. So this is nothing but butanol. For butanol, primary alcohols 2 are possible. How? So this is 1, 2, 3, 4. This is primary alcohol, and one more possible with the same compound is this. So this is 1, 2, 3, 4. So this is primary, this is also primary. Total 2 are possible. Primary and secondary tertiary amines are functional isomers. So that is amines NH2, C, N, C, this is secondary, this is primary, and another one is this. So this is tertiary. All these are functional isomers. Which of the following compounds is isomeric with trimethylamine? Trimethylamine is nothing but again same. So primary and secondary, that is 1 propanamine, 2 propanamine, both will come. So this is related to the second question only. Which of the following classes of organic compounds show metamerism? Ethers, yes, ethers will show. Secondary amines also will show. Ketones, all of them will show metamerism. Among the following, the pair that is not a pair of metamers. So here metamers are shown by, again, ethers. First option will come, same molecular formula is there. Second is also same, but third one is not a metamer because number of carbons are less in the second compound. Which of the following can show geometrical isomerism? To show the geometrical isomerism, we know the conditions, right? So what is the conditions? There should be double bond at the same time. Two identical groups should present, and that identical groups should present on the adjacent carbons, not on the same carbon. So now let us see here. First compound 2, 3 dimethyl butane, let us write. So first compound is 2, 3 dimethyl butane. Here there is no what you call double bond, so it cannot show. Next 2, 3 dimethyl 2 butene. 2, 3. So here methyl group, that is identical groups are on the Me is nothing but methyl group. On the same carbon, identical groups on the same carbon cannot show geometrical isomerism. Next one is 1, 2 dimethyl cyclohexane, third option. So cyclohexane is this, and 1, 2 is said, right? Yes, H, and here methyl, it will show cis trans isomerism. Third option will come. 2 methyl pentane, pentane, this is an alkane, will not show geometrical isomerism. Sixth, third one is the answer. Next, let us see the number of chiral centers in the given compound is. Chiral center is nothing but carbon which contains 4 different groups. 4 different groups. Then that carbon is called as chiral carbon. This actually generally we discuss in optical isomerism. So here this carbon is having 4 different, and this is also having 4 different groups. Why? Because here one more is hydrogen. To satisfy the tetravalence, you have to write hydrogen, right? So hydrogen is one group, methyl is one group, right? And this part is one group, and this part is one group. Total 4 different groups are there. So like that, 2 are possible chiral centers. Number of geometrical isomers for the molecule is given here. If you observe, this molecule is a symmetrical molecule. Why? Because the terminals are having same, and we know how to find out number of geometrical isomers for symmetrical and unsymmetrical molecules with even number and odd number of double bonds. If you observe this is a symmetrical molecule with odd number of double bonds. Here 1, here 2, 3 double bonds are present. So the formula to calculate number of geometrical isomer for this type of compound is 2 to the power n minus 1 plus 2 to the power n minus 1 by 2 is the formula. So that is equals to 2 to the power. So here n is nothing but number of double bonds. Total how many are there? 3 are there. Minus 1 plus 2 to the power 3 minus 1 by 2. That is equals to 2 to the power. This is 2 plus it is 2. 4 plus 2, 6. So 6 isomers are possible. Next, coming to the 9th question, that is benzaldehyde can exist in two geometrical isomeric forms known as, so that is syn and anti. Why? Because the molecule we can represent like this, that is benzaldehyde is said. So CH double bond NOH. H and OH both are on same side of the double bond, then that is called as syn and anti-isomerism. Next, here how many structural and geometrical isomers are possible for dimethyl cyclohexane? Dimethyl cyclohexane, how many are possible is asking. Let us see. So here dimethyl cyclohexane is nothing but, so this is for example here and here methyl groups. So this is ortho, meta is also possible and para is also possible. So here ortho, meta, para. Along with that, even two methyl groups can present on the same carbon like this. Okay, so total number of isomers, how many are there? That is what you call structural isomers. Structural isomers 4 are there. Structural isomers are 4. Next, geometrical isomers also is asking. How many geometrical isomers are possible here? So totally 3 isomers are possible. That is 3 cis, 3 trans. How 3 cis, 3 trans is possible? So let us see how it is possible. I'm writing here. So this is dimethyl, H. Here one methyl group, here one methyl group. This is cis at 1, 2 position. Cis at 1, 2 position. Same way 1, 3 position cis trans is possible. Okay, and 1, 4 position. So this is 1, 2, this is 1, 3 position, this is 1, 2, 1, 4 position. So 3 cis, if cis is possible, trans is also possible, right? So 3 cis, 3 trans, total 6 geometrical isomers and 4 geometrical isomers 6. So the answer is what? 4 and 6. Second option is right. Next, which of the following pairs of compounds is a pair of enantiomers? First, enantiomers are nothing but the isomers which are mirror images but not superimposable. Not superimposable. Then they are called as what? Mirror enantiomers. Enantiomers are the isomers which are mirror images but not superimposable are called as enantiomers. So in these compounds, which are the enantiomers they are asking. So first compound if you take, and one more point also we can discuss, the compound in which plane of symmetry is possible, right? Plane of symmetry is possible, they are not considered as isomers. So here in the first case, so these are the what mirror images but it is not considered as enantiomer. But second one is mirror image, that is if you place a mirror here, they are looking like a mirror images but they are not superimposable, so that is considered as enantiomer. Even 3 is also not possible, 4 is also not possible. Second option is correct. Next, The maximum number of optically active stereoisomers that could exist for the compound below is maximum number of optically active. When a compound is optically active, when it contains four different groups. Four different groups. That is only called as chiral center, generally will say. Okay. So in the given compound, let us see here four different groups are present on this carbon. How this side CH3 group is there, Br, and here hydrogen is there because tetravalence we have to see, and this remaining group is one group, right? So that's why we can say there are only four different groups are present like this. Same way here also four different groups, here also four different, here also four different groups. Total how many chiral carbons? Four chiral carbons are present, right? Right? But whatever this is there, this is not a chiral because two hydrogens are present on the same carbon. Around carbon there should be four different groups, then only it is considered as chiral carbon, right? And see, in this molecule there is a symmetry. There is a symmetry in this molecule. Okay, for the symmetry molecule with the even number of and odd number of symmetry molecules, right, with the even number of chiral center with the odd number of chiral center, we have different formulas. For even number of molecules, the formula is 2 to the power n minus 1. For odd number of molecules, this formula we already know, 2 to the power n minus 1 plus 2 to the power n minus 1 by 2. So here in the given molecule there are four different, that is chiral carbons are present, that is even. Then the formula used is 2 to the power n minus 1. So 2 to the power n is equals to 4 chiral centers, no, minus 1, that is equals to 2 to the power 3, that is equals to 8. 8 is the answer. Now clear, no? Next let us see question number 21, that is the chirality of the compound, that is CH3CBrHCl is. Actually this is also we have to discuss RS configuration, but anyways I'll try to explain. Just listen. I'm giving priority order. In the all compounds we are giving least priority to hydrogen. Four groups are there, no, around carbon. First priority is given to bromine because its atomic number is more, then chlorine, then methyl group. Okay, so in giving the RS nomenclature, always least priority group should be in the bottom position. That means you have to take 4 or you have to write 4 bottom, then shift this 2 here. Don't change the position of 1, just change the position of 3 to the rightmost part, so that you will get like this. Here 4th, 2 shifted to left side, 1 at as it is position, and 3 shifted to extreme right. Now see whether it is clockwise or anti-clockwise. If it is clockwise, R is assigned. If it is anti-clockwise direction, the numbers are moving, then it is S configuration. Now let us see. 1, 2, this is anti-clockwise. That's why the configuration is assigned as S. This we'll discuss once again in the classroom. Got it? Next. So 25th question, let us see. Remaining questions actually we have to discuss in the class. 25th, this is related to, just now we discussed the same question, that is E and Z isomerism. So here H and OH both are same side of the double bond, that's why it is a syn isomer, we can say, right? Which isomer? Syn isomer. Next question number 30, let us discuss. Here this is the compound. In this, what type of isomers are possible, or these are what type of isomers he is asking. So these are the geometrical isomers because double bond is there. Okay, so double bond containing compounds will show geometrical isomerism. Next 31, the boiling point of cis 2-butene is more than trans 2-butene. Yes, this is correct. Next, Cis 2 butene is more polar than trans. Yes, polarity is more for what you call cis 2 butene. So both are correct, and R is the correct explanation of A. Next, let us see 32. Lactic acid is optically active compound. Yes, lactic acid formula is, what is the formula of lactic acid? CH3 CH OH COH will write, right? So CHOH COH. So around carbon there are 4 different groups are present. One is methyl, other one is acid, other one is what, hydrogen, and this is 4. Fourth group is OH. 4 different groups are present, so it is optically active. Correct statement. Next, it contains a chiral center with plane of symmetry. There is no plane of symmetry. This is wrong. So A is correct, but R is false. Third one is right. Plane of symmetry. Plane of symmetry means if you write a plane which bisects a molecule into 2 equal halves, it is not possible because 4 different groups are present. Symmetry is not present. That's why R is wrong, you can say. Next, conformational isomerism. Draw the Newman projection formula of most stable conformation of, what is asking, 3-hydroxypropanol. It is stable due to, yes. So I am drawing the structure of 3-hydroxypropanol. What is 3-hydroxypropanol structure? Here, right? 3-hydroxypropanol is said. So here I'll draw 3-hydroxypropanol CH3 propanol. So you can write it as what? CH2 CH. So number starts from here 1 2 3, then this becomes OH 3-hydroxypropanol. Sorry, propanol is said, that's why aldehyde group you have to take. This should be CHO, and this should be H, and here also H. Okay, now this is CH2OH. I am writing Newman projection formula. In the Newman projection formula, here we have OH, and next here it is H. Okay, and one more I am taking, that is which contains C double bond O H aldehyde, here H, here H. Now between this H of OH group and O of ketone group, there is a hydrogen bond is present. Chelation is possible, stability increases, right? So that's why that is more stable. Okay, the stability is because of what? Intramolecular hydrogen bond. Intramolecular hydrogen bond. Next, in the given conformation of C2 is rotated about C2 C3 bond anti-clockwise by an angle of 120 degrees, then the formation obtained by the former, that is nothing but conformer obtained is formation, not formation, that is a conformer obtained is. So rotation by what? C2 C3 is asking n-butane. Just today only we discussed now. C2 C3 rotation is possible in that at 120 degree rotation in anti-clockwise is saying. Anti-clockwise means, okay, this is 60 degrees if you rotate. What type of compound is formed? This is as it is, front carbon is as it is, H, but 60 degrees rotated means this one coming here, this goes here, this comes here. So the compound becomes, I'll write with the C. Here CH3 will come, then here H will come, and here H will come. Again 60 degrees because 120 is said, no, right? So again 60 degrees if you rotate, then you are getting, okay, so here CH3 will come, here H will come, here H will come, whereas this is as it is, no, CH3 because we are rotating backside carbon. Okay, now this is 120-degree rotation. The 120-degree rotation, what conformer is formed? This conformer is called as, which conformer? Gauche conformer. So third one. So it is a Gauche conformer is possible. Next, let us see the dihedral angle between two methyl groups in partially eclipsed conformer of N-butane is. Partially eclipsed conformer, the dihedral angle between two methyl groups is how much? 120 degrees. Right, this is 120 degrees. Second option is correct. Right, partially eclipsed means what? The structure I will show here also, 35. Okay, partially eclipsed, CH3 H. Right, now if you rotate, hydrogen is here, CH3 is here, another hydrogen is here. Okay, now this is 120 degrees. 120 degrees, right? Next, 36th. In the Newman projection formula of the least stable staggered form of N-butane is. Least stable staggered conformation, right? Which of the following reason is the cause of its instability? Van der Waals strain, right? Due to Van der Waals strain, it is vertical least stability, we can say. So these are the questions from exercise 2.